Hello, welcome to Econometrics Melody. In this video, we will talk about the distribution of sampling statistics. Now, we are going to take the sample from population and we want to calculate the mean and variance from the sample and we want to infer it to the population. So up to this point, we have seen that the random variables, they have a different kind of distribution, or they can have different kind of distributions, and the distribution exists for the random variable, and we can calculate some parameters for the population, like the expected value of it, as well as its variance, and special attributes or the defining attributes of the sample. We call it as statistics. For the population, we call it as parameters, and the most widely used parameters for the population are mu, representing the mean, and sigma square, representing the variance. And for the sample, the mean is represented by x bar and the variance is represented by s square. Similarly, when we know the distribution of the population, and if we want to infer the parameters of population by the help of the statistics from the sample, then that case is called as the parametric inference. While if we don't know, or if we cannot assume anything about the distribution of the population, and the distribution is either unknown or unidentified, the distribution cannot be assumed properly, then such case is called as non-parametric inference. And also we have seen that for two independent events x and y, the expectation of xy can be expressed as the product of their individual expectation, and in that case the covariance of xy is equal to 0. And further, we know that as the covariance between xy is equal to 0, so the variance of the sum is equal to the sum of the individual variance in case of independent events, two independent events x and y. Also, we know that the variance is affected by the square of the scale, so variance of ax is equal to a square variance of x. Now let us continue with our today's topic. It is about the sample mean, and we know that for the parametric inference, we know that the distribution of the population is well defined or identified, or we know about the distribution of the population and their parameters. The important parameters into consideration are the mean, that is represented by mu, and the variance, it is represented by sigma square. From this population, if we take n number of samples and the samples are represented by from x1 all the way to xn, then the sample mean, this is x bar, this is equal to the sum of the observations, and we divide it by the number of the observations. Now let us take the expectations on both the sides. Then we are left with expectation of x1 plus, and also we know that expectation of the sum is equal to the sum of the expectation, as well as the expectation of the constant is the constant itself. So let us take 1 by n outside and let us write it as expectation of x1 plus. So this is equal to, and as we have drawn the sample from this population, the expectation of which is equal to mu, so all the expectation we can write it as mu. So our sample size is n, so this should be equal to n into mu, and n and n, it cancels out, this is equal to mu. Therefore the expectation of the sample mean is equal to the population mean. So in this case, we call it as an unbiased estimate. In other words, we can say that the sample mean is the good representative of the population mean. Now let us calculate the variance of the sample mean. So we know that variance of our sample mean is represented by, so this is equal to, and we have seen that variance of ax, this is equal to a square x, and for any independent event x and y, we know that the covariance of xy is equal to 0. So in this case, age x1 and x2 all the way to, they are independent. Therefore the covariance of the possible pairs, let us say they are equal to 0. So any number of pairs. For any two independent random variables x and y, we know that the variance of their sum is equal to the sum of their individual variance, because the covariance between them is equal to 0. Now applying this two property, what do we get? So 1 by n, each n is constant, so this is equal to 1 by n square, and we have variance of the sum of the independent random variables, so this is equal to the sum of their variance. And we know that this sample comes from a distribution with the parameters mean, age, mu, and variance is sigma square. So variance of x1 is also sigma square, and the variance of each random variable, this is equals to sigma square. So this is equal to 1 by n square, and we have n number of sigma square. So this is equal to, therefore, variance of x bar, this is equal to variance of the variance of the sample mean, this is equal to sigma square divided by n. So we have seen that the sample mean is also centered. If this is the center of the population with mean mu, then the sample mean is also centered in the population mean mu. If this spread represents the variance, then for the sample mean, the spread is somewhat less than the population. And for the time being, let us assume that the sample mean has the same distribution as that of the population. Then the sample mean has the less variance than the population. So let us see the variance of the sample mean, and if n increases, that is n gets larger, and this is our variance of sample mean. So for large n, variance of sample mean decreases. So we can decrease this spread by increasing the sample size, or we can decrease the spread of the variance, or that is the variance of the sample mean. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Malade.